Hey, physics peeps, we're coming to the end of this chapter, and I wanted to do kind of a quick summary for you of the things that we covered in this chapter. So if you remember, we looked at point charges, and we said there's an equation that goes with that is F equals QVB, where F is the force acting on the charge. Q is a test charge that's being shot into or moving through a magnetic field. And then V is a velocity of that test charge. And B is magnetic field measured in Teslas. Magnetic field measured in Teslas. Remember that will give you the magnitude or the number value of any one of those. Then if we want to find the direction, we have to use the first right-hand rule. First right-hand rule. So what I'm going to do is, let's see, how about we give you a simple problem. We'll do X, 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 X. Set up a magnetic field here that is going into my desk or into the screen. And let's say that we have an electron that is moving from west to east. So remember that for the right-hand rule, you're going to use your right hand. Your thumb goes with the velocity, fingers go with the field, and your palm is going to go with the force. So I'm going to take and finagle my hand so that the fingers are going into the desk. My thumb is going in the direction of the velocity, and because it's an electron, it will be going into my palm. And so the answer for this one is going to be this direction, which is south. So we would say that the force on the electron is heading in the south direction. Force is heading south. So remember, fingers field, thumb velocity, palm force. Remember that you could sometimes see it as this way, where you would have your three axes represented that way. But what we did was we used the palm for the force, fingers for the field, and thumb for the velocity. Okay. The next one that we looked at then was we took these wires and we said, hey, if I take and I want to find the force on a wire, this is going to be through the equation F equals ILB. And F again is going to be a force. I is going to be a current. And remember that current is nothing more than how much charge you have flowing in a certain amount of time, or Q per T, I should probably use instead of S, Q per T. And then L is going to be a length. That's the length of the wire. And B, again, is the magnetic field that the wire is in. Now, interestingly enough, this is not a super complicated derivation. We could literally take this F equals QVB and say F equals QVB. Remember that velocity is nothing more than our distance over time. So I could say a length over a time times B, Q equals F. And if I move my T over and do Q divided by T over there, then you can begin to see where that sets up, where I can say now my Q over T is my current, my length, and my field, and that's sort of where that F equals ILB equation comes from. Okay, moving on. The field around a wire then, another dude came up with this. His name was Ampere, so we came up with Ampere's law, that is B equals mu naught I over 2 pi r. So B, again, is the magnetic field, and I is still the current, and R is the radius. And then the new thing that you probably don't recognize or are not sure about is this mu naught value. So remember that the mu naught is a constant, and that constant is 4 pi times 10 to the negative 7. So if you remember, originally we had the k q over r squared, and the k was the constant, and we thought, hey, that's going to be the constant for electricity and magnetism. Well, it turns out that this mu naught is a more fundamental value, or a more fundamental constant, and the k is actually related to that mu naught. And that value shows up in a lot of magnetic equations. It shows up in a lot of electric equations. And because light is an electromagnetic wave, it shows up in the light, some of the light equations also. Another thing to notice is that this 2 pi r is really, if you remember, a circumference. So whenever I look at this, so let me jot down here again that this is Ampere's law. So whenever I look at this, I have this wire that maybe has a current that's flowing this way. And what Ampere discovered was, he said, hey, there is, when we run this current through the wire, it creates a magnetic field around it, which isn't too hard to think about, because if you think of current is really the flow of the electrons, and magnetism is the spin of the electrons. So doesn't it make sense that if I have a whole lot of electrons flowing through this wire here, they're going to start rolling over each other, which is going to give them a spin, and that may or may not, but that kind of mentally is a way to think of it, and that would give a magnetic field that's around the wire. And so we end up with this field that's created around the wire here. And if you think through the circumference, it's spreading that magnetic field out over whatever that circumference is. So if I have a tighter circumference, I'm going to have a much stronger field. If I have a wider circumference, I'm going to have a much weaker field, because those are inversely related. So the bigger the radius, the bigger the circumference, the smaller the magnetic field is going to be that way. One of the ways you can think of it is if you think of it as like a flashlight, where if I have a flashlight shining on my page and I'm really, really close, I have a really bright, intense dot right where that light is. Well, as I move my light away and I'm spreading out the same amount of light over a much bigger area, it's going to become much dimmer. And that's really what's happening here too, is I have the magnetic field getting spread out over that circumference. Now, the way that we have to find the direction for this is going to be the second right-hand rule. So remember that for the second right-hand rule, our fingers still match the direction of the field. Our thumb still matches the direction of the flow of the charge, which in this case is the current. And so if I have a wire that is flowing, where the current flows from down here to up here, I would grab the wire so that my thumb is going in the direction of the current, and my fingers curl in the direction of the magnetic field. So the magnetic field will go around the wire this way, counterclockwise. Same thing down here. If my wire is going this way, the current, then I would literally grab the wire so that my thumb is in that direction and curl my fingers around so that it's coming around the wire in the way that I drew that arrow there. Now, the trick on these is just to kind of pay attention to where the question is asking you. Like if it says, what's the direction of the field over at that point there to the right of the wire, then I would grab the wire and turn my fingers so that my fingers are to the right of the wire. And at that point, they're going into the page. So I put a big X there, or say in. If it's asking over here on the left side of the wire, I would grab the wire and put my fingers on the left side of the wire. And at that point, it's coming out of the page. So I'd put a big dot there, or say out of. If we're talking above the wire, then I'm grabbing the wire, and up here all the way above, so I'm twisting out of the screen here, up here above the wire, then they're heading that way, which means that they would be going above the wire, they're heading to the east, and behind the wire, then they're heading that way, which is to the west. And you can see that that is that counterclockwise loop that I was talking about. That also applies, you will see that over here into this whole wire area. So it works both ways for both of those for the second right-hand rule. Okay, now moving on to generating electricity, we want to talk then about Faraday's law. So remember that Henry and Faraday's law discovered that you can take magnetism and create electricity. So all the way back, Oersted discovered that you can take electricity and it will create magnetism. And Henry and Faraday discovered the other way, that you can take magnetism and create electricity. So the voltage then is equal to the magnetic field times the area over the time. And it's really the change in field over the change in time, or the change in area. It's the change in any of those, which means something has to be changing or something has to be moving. Okay, so uppercase V, remember that uppercase V is our representative of voltage. Uppercase B is magnetic field. We already talked about that one a couple times here. Field, field, and field. A is going to be an area, the area of the loops that we're talking about. And then T is going to be time. T is going to be time. So in essence, what we're doing is we're taking a set of loops here. So this is going to be loops of wire. And then we're going to take a magnet, north and south. So there are a couple different things that we can do with this. We can either take, if I have these loops of wire, remember that our magnet is strongest at the poles. So all the way away from the magnet, pick something you can see the color, all the way away from the magnet, It's a really weak field here, a really strong field here. So if I'm moving my magnet into and out of these loops, then the field is getting stronger, 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 weaker, 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 weaker. And because that field is changing with respect to time, the area is not, but the field is changing with respect to time, then we induce a voltage across that wire, which will make the current flow through it. The other thing, so what we could do is we can move this compass in and out, or the magnet in and out of the loops of wires. Now, the other thing we could do, if you think about the concentric circles that are the magnetic field around this, is couldn't we take and rotate the magnet? So if I take this magnet and I spin it, then I'm constantly changing the north-south values that are or fields that are coming through the area of that loop, and that will also be a change in field per time, which will induce a voltage. And that is, whenever you built your wind turbines, you had to do one of those two things, where you either moved the magnet with respect to the wire, or the wire with the loops with respect to the magnet, or you rotated your magnet inside your loops, and that generated the electricity or induced the voltage. For those of you who did the speaker, you did the opposite. You connected this to your headphone jacks, and then whatever is producing your music, whether it's your iPod or iPhone or your computer or your whatever phone it is that you have, then that's going to change the voltage, change the current, which changes the magnetic field in that loop of wire, and that causes this magnet to attract and repel and vibrate, and that vibration vibrates the cup then, or the plate or the bowl that you had connected to the magnet or the wire, and that vibration is the sound that you hear. And so you're taking that electricity and converting it into the vibrations that you have. Any way that you look at this, one thing that you have to be sure of when we talk about this inducing electricity is that one of those must be moving. That energy has to come from somewhere. You can't just literally take the magnet, sit the magnet in the wire, and boom, we have electricity. It doesn't work that way. The way that it comes from is that motion, that kinetic energy, is really being translated into the electric energy. Now think through, all of our society, or almost all of our society, is based on that, where this is some sort of magnets hooked up into a loop inside a loop of wire on an axis that has a blade. And as that blade spins and those magnetic fields are going across all of those loops, that is generating some form of electricity that is coming out to your house. And it doesn't matter how we generate that. Maybe there's coal down here that's burning and the rising heat causes this to spin. Maybe it's nuclear and we have the steam from the hot water coming up and causing this to spin. Maybe this is hydroelectric and the water is coming down and spinning that. Maybe this is a wind turbine that's elevated up in the air and the wind is causing that to spin. But at its heart, all of those have a generator where you have these sets of magnets that are inside the wires, and we have a changing field per time that is inducing a voltage for that. The only one that you could say that is not necessarily that way, or one of the big ones that you would say that, would be if we're talking like solar energy, where we have a photovoltaic cell. There is not a fan blade and not a set of magnets or whatnot. So as a whole, this is what we've covered in the chapter. I hope this gives you a good review for what we're doing. We have point charges, QVB, and the direction will be first right-hand rule. We have wires, ILB, that you can use the second right-hand rule to find directions, and or you can use Ampere's law, mu naught I over 2 pi r. And then we have Faraday's law, which is the magnetic field changes. When the magnetic field changes across the loops, then we induce a voltage on that. Take care.